Hello, everyone, and welcome back to this being week 3 Wednesday. So, this is the material for my Chem 1520 class that we missed due to the great snowstorm of January 2026. So, just like I would do in class, we are going to start off with a step back. So, this step back is regarding Clausius-Clapeyron and just some other random stuff. So, like I would do if we were in class, I would set this up before I go get my water and whatnot. And so for right now, what I want you to do is hit that pause button and try to solve this on your own before I walk you through it. So we've got two questions going on here. And question number 1 has many various and sundry parts. So for number 1, we're talking about dimethyl ether, which has the molecular formula of CH3O, CH3. It has a vapor pressure of 1 atmosphere at negative 23.7 degrees Celsius. So that's the amount of gas above the surface of the liquid at negative 23.7 degrees Celsius is 1 atmosphere. And at half an atmosphere, 0.526 atmospheres, a vapor pressure above the sample, it's 37.8 degrees Celsius. So what is the normal boiling point of dimethyl ether? You don't actually have to calculate anything. What phase is dimethyl ether at room temperature, solid, liquid, or gas? A little bit of a throwback, trying to remind you guys about temperatures and room temperature and phase changes. What is the equation? This is going to be the tough one. In my opinion, this is the hard question. What is the equation that corresponds to the delta H of formation? Delta H of formation for dimethyl ether. That is different than the delta H of fusion. Delta H of fusion is the enthalpy change when something either freezes or melts. This is the delta H of formation, where it is the energy change. Oh no, I lost my. There we go. It's the energy change for the formation of 1 mole of product from its elements. Product, compound, I'm not sure exactly what term I want to use there. And then lastly, the new stuff, or the stuff that's important-ish, is, or for 1520, what is the delta H of vaporization of dimethyl ether? And we are going to use the Clausius-Clapeyron equation for that. The Clausius-Clapeyron equation is the natural logarithm of P2 over P1 equals negative delta H of vaporization divided by a gas constant in the right units times 1 over T2 minus 1 over T1. The most important part of the Clausius-Clapeyron equation is the vapor pressure that's on top in the natural logarithm matches the temperature that comes first. The vapor pressure that's in the bottom matches the temperature that comes second. That is the utmost crucial thing. And then question number 2, at what temperature is the vapor pressure of water? 40.1 millimeters of mercury. The delta H of vaporization of water is 40.7 kilojoules per mole. So that's another place that you're going to need the Clausius-Clapeyron equation. And just in case you have forgotten, there are 760 millimeters of mercury in every 1 atmosphere. And the gas constant, we know it from last semester dealing with the gas laws, of 0.0821 liter atmospheres per mole Kelvin. But this semester we're going to be using it in its energy terms, 8.314 joules per mole Kelvin. So watch your units, take a pause here, try to calculate, and then of course, and as always, I will show you. Okay. So, what is the normal boiling point of dimethyl ether? The normal boiling point of dimethyl ether is negative 23.7 degrees Celsius. Remember, the definition of boiling point is the temperature at which the vapor pressure matches atmospheric pressure. Normally, normal boiling point is the temp at which the vapor pressure equals 1 atmosphere, basically at sea level, because we're not up in altitude. As you go up in altitude, that changes boiling point. Normal boiling point assumes that you are at sea level. Sea level is 1 atmosphere of pressure pushing down on you. So the normal boiling point is the temperature at which the vapor pressure equals 1 atmosphere. So write in the question 1 atmosphere at negative 23.7 degrees Celsius. What phase is dimethyl ether in at room temperature? So here's our like number line. And we have the melting point, which again is the same as the freezing point. It just talks about which direction it goes in. And then we have the boiling point. If you're less than the melting point, then you are a solid. If you're between melting and boiling, then you are a liquid. If you are above boiling, you are a gas. So we have what phase is dimethyl at room temperature? Room temperature is approximately 20-ish degrees Celsius. Okay. So I'm so sorry. I just lost my train of thought, like hardcore. Um, whew. The melting point for this. Oh, I'm sorry. I got it. The boiling point for this is negative 23.7 degrees Celsius, above which it's a gas, below which it's a liquid and a solid. So dimethyl ether at room temperature, we are well above that boiling point. We're well above negative 23.7 degrees. And so that means that this compound is a gas at room temperature. Sorry, I kind of lost my brain there for a second. What is the equation that corresponds to the delta H of formation of dimethyl ether? So this is again from last semester. And what we did is we said, all right, we're going to form 1 mole of the compound from its elements. So I'm going to rewrite dimethyl ether in like normal terms. This is trying to show you the connectivity of things. This is trying to show you that you have a carbon with 3 hydrogens around it. It's trying to show you like what the Lewis structure looks like. Bonded to an oxygen, bonded to a carbon that has 3 hydrogens around it. So it's trying to show you what it looks like. So it's a chemical formula for sure, but it's an interesting one because it's trying to show you what the Lewis structure looks like. I'm going to write this in just like normal chemical molecular formula terms. 2 carbons, 6 hydrogens, 1 oxygen. So we're going to form that from its elements. So first off, we have carbon. Elemental carbon in its most stable state is a graphite. We'll worry about balancing it in a second. Next up, we have hydrogen. Hydrogen in its elemental state comes as a diatomic H2. And then last, but certainly not least, we have oxygen. Oxygen in its elemental state is O2. So now we have all of the elements that form our product. Now we balance it. We cannot change the coefficient in front of this because we are saying that it is the delta H of formation. Delta H of formation is always 1 mole. This is the only time you can use fractional coefficients. So we need a coefficient of 2 in front of the carbon to balance that out. We need a coefficient of 3 in front of the hydrogens to balance that out. And in front of the oxygen, we have a 1/2. This is the only time you can use fractional coefficients. It has to do with formation of 1 mole of compound from its elements. So this is the equation that corresponds to the delta H of formation. And now, what is the delta H of vaporization of dimethyl ether? Let us solve some Clausius-Clapeyron. So we have one set of things. We know 1 atmosphere and negative 23.7 degrees goes together. We know 0.526 atmospheres goes together with 37.8. So the natural logarithm of P2 over P1 equals negative delta H of vaporization. That's what we're solving for. I'm just going to even simplify it further and just call it X, divided by 8.314, better known as R. Yeah, let me erase that. Let me write it out first, and then I'll plug variables in. times 1 over T2 minus 1 over T1. So, again, most important thing, it doesn't matter like what's on top and what's on the bottom. We can have P2 be the pink one and we can have P1 be the blue one. It doesn't matter as long as they go in pairs. Whatever is on top in the fraction around the natural logarithm must be the first term in that subtraction. So let's say that P2 therefore is pink. So P2 is 0.526 atmospheres. And that's the vapor pressure at 37.8 degrees Celsius. Our next set of pressure and temperature is we have 1 atmosphere at negative 23.7 degrees Celsius. Delta H vaporization is what we're solving for. R is 8.314 joules per mole Kelvin. Make sure your units make sense. Like, don't just start plugging things in until and unless you make sure that your units match. So our R is in terms of joules per mole, which means that my X is going to be given to me in terms of joules per mole. Most of the time, delta H's of vaporization are given to you in terms of kilojoules per mole. So just keep in mind, this has to match that. What's next? Our units on our pressures match. That's fine. It doesn't matter what they are, millimeters mercury, torr, atmospheres, as long as they're the same, because you divide them, so you want them to cancel, so they have to be the same. Last but not least, this has to be in terms of Kelvin. So I'm going to add 273.15 to both sides. Let me grab my handy dandy calculator. 37.8 plus 273.15. 310.95. Oh no, something bad has happened. Oh no! I typoed this. Yeah, this makes no sense. I'm so sorry. The vapor pressure has gone down, which means that the temperature had to have gone down as well. This is negative 37.8. This doesn't make any sense. Well, I'm going to leave this in just so you guys know that this makes no sense. So I typoed. There's clearly a typo. I missed the negative sign. So how did I know that? 1 atmosphere, that's the amount of gas above the liquid at negative 23.7 degrees Celsius. So you have 1 atmosphere at negative 23. You have less when the temperature goes smaller, okay? And I think that that's why I was like struggling with the one earlier, the solid liquid gas one. I think my brain was like, what is happening? This makes much more sense now. The atmospheres, the vapor pressure above the surface of the liquid is less. We went from 1 atmosphere to 0.5 atmosphere, so it had to have gone down. The temperature had to have gone down in order for that to have happened. All right, so let us put in that negative sign. My deepest apologies. Negative, oh, what happened? Here we go. Oh, my calculator. Negative 37.8 plus 273.15 is 235.35 Kelvin. Now we're cooking with gas, as they say. Negative 23.7 plus 273.15, 249.45. All right, now like all of my units make sense. I'm ready to go. I can start doing the algebra. So we have the natural logarithm of, and again, can't stress this enough. The pink on top goes with the pink that comes first. So this is the natural logarithm of 0.526 divided by 1 equals negative x. Don't lose the negative sign. That's really, really, really important. Divided by 8.314 times 1 over at 0.526, 235.35 Kelvin, minus 1 over at 1, that's on the bottom. That means it's going to come in my second term, 249.45. Excellent. Now, again, if you get to this point, my friends, you're over halfway there. Now we're just doing some algebra. So now let me talk you through my algebra. The first thing I'm thinking is I don't need e to the power of at all. The natural logarithm of 0.526 is just a number. So on my calculator, literally, natural logarithm 0.526. And we get negative 0.64245. And remember, don't lose a lot of your digits. Like keep many, many, many of your digits. In particular, when we get really small values, which is what you get when you have 1 over 235 minus 1 over 249, you get really, really small numbers. And so you need to make sure that you keep your digits so that the rounding errors don't really compromise you too much. That equals negative x over 8.314. I'll deal with that in my next step. Times 1 divided by 235.35, enter, minus parentheses, 1 over 249.45, close parentheses. I got 2.4017 times 10 to the negative fourth. Let me just double check and make sure that makes sense. Yeah, it's not a negative number. It's small. We're good. Now, this is again where I start to panic about how to do orders of operations because it's been a minute. I'm going to multiply both sides by 8.314. That gets it out of the denominator. So negative 0.64245 times 8.314. I got negative 5.341 equals negative x times 2.4017 times 10 to the negative fourth. Divide both sides by negative 2.4017 times 10 to the negative fourth. 17 times 10 to the negative fourth. Negative 5.341 divided by negative 2.7 times 10 to the negative fourth. You get that x is equal to 22238. Again, we've got to finish this. Don't think that this is the end, my friends. You have to do more. First thing we have to do is worry about significant figures, okay? 1.00 is 3, 23.7 is 3, 3. Okay, it's me. We're going to round this to 3 significant figures. So we have 22,200. What are the units? Joules per mole, because we're talking about the delta H formation. So you can either leave it for me, you can either leave it as 22,200 joules per mole, or you can take it and say that it's 22.2 kilojoules per mole. There is the wonderfulest Clausius-Clapeyron equation. All right, what is the next one? At what temperature? So I'm going to color code this in pink. Is the vapor pressure of water 40.1? Those two things have to go hand in hand. So we know we're going to be solving for a temperature. And just for funsies, for no good reason, I'm going to label it as T2. It doesn't matter. It could be T1. It doesn't matter as long as these two things go hand in hand. And the reason I do T2 is because it's on top. P2 is on top. T2 is the first one. Don't ask me why they decided to make the equation that way. It is what it is. We're going to use it again coming up when we start talking about kinetics, and it's going to be formatted exactly the same way. So at least we get consistency between this Clausius-Clapeyron equation and what we will eventually use in the kinetics portion. Just make sure that they go hand in hand. Don't mix up what's on top and what comes first in the equation. All right, we have the delta H of vaporization of water is that. So let's set this up. So the vapor pressure is 40.1 millimeters of mercury at some kind of temperature. All right. So then we need a pressure and a temperature. And again, you're like, Oh God, she hasn't given me enough information. The delta H, I have, just so you guys know, I have given you enough information, I promise. I know I typoed on the last slide, but I didn't make a mistake this time. The delta H of vaporization is 40.7 kilojoules per mole, and our gas constant is 8.314 joules per mole Kelvin. Okay, so the biggest thing I'm going to tackle right now is this whole what's my second set of pressure and temperature? And it is again that whole normal boiling point thing. The normal boiling point of water is 100 degrees Celsius. So at 100 degrees Celsius, the vapor pressure of water is 1 atmosphere, which is 760 millimeters of mercury. So don't lose that normal boiling point thing. We know what the normal boiling point of water is. I didn't need to give it to you. I didn't need to explicitly state it. It's something that you know. All right, let's double check now and see if we're ready to put things in the equation. Our pressure units are the same, so that is exactly what we want. Our temperature units, obviously, we have to convert it into Kelvin. So that means our answer is going to be in terms of Kelvin. That's fine. Now, our delta H of vaporization is in terms of kilojoules per mole, but that doesn't work because our constant is in terms of joules. So we're going to go from kilojoules to joules. Every 1 kilojoule is 1,000 joules. Just in case you're like, Dr. L, where are you getting that from? That's metric system. Kilo has always been, for every 1 kilo, there's 1,000 base units. So for every 1 kilometer, there's 1,000 meters. We've done that for forever. So 40.7 times 1,000. Don't ask me why I'm doing this on my calculator right now. 40,700 joules per mole. We're ready for the Clausius-Clapeyron equation. And where do I want to put? I'll keep going over here. The Clausius-Clapeyron is the natural logarithm of P2, 0.1 millimeters of mercury, over P1, 760 millimeters of mercury, equals negative delta H of vaporization, 40,700, divided by 8.314 times 1 over T2. That's what we're looking for. I'm going to leave it as X. You could write it in as T2, whatever makes you happy, minus 1 over T1, which is 373.15. Again, you get here, over halfway there. Now we just got to solve the algebra. Again, something that I am thinking to myself is, I don't need e to the power of both sides. The only time you need e to the power is when the natural logarithm has a variable inside it. So like this, you need to take e to the power of both sides to undo the natural logarithm. Here, within the natural logarithm, that has a term. I've been trying to figure out what that term is. But whatever comes after that natural logarithm, there's no variable in there. So the natural logarithm of 40.1 over 760 is just a number. So on my calculator, natural logarithm of 40.1 divided by 760 gives me negative 2.942. That equals negative 40,700 divided by 8.314, just a number, negative 4,895.36 times 1 over x minus 1 divided by 373.15 is, guessed it, just a number. Don't lose your digits. 0.00. I'm running out of room here. 26. Oh, geez, it's long. Oh, let me try to cram it. 0.00268. There we go. All right. So now again, I don't know why I just shut my calculator off. We've got more stuff to do. All we're trying to do is isolate that x. The very first thing I'm going to do, resist the urge to distribute. We're going to get rid of it by dividing both sides. Divide both sides by negative 4,895.36. So negative 2.942 divided by negative 4,895.36. I got 6.00977 times 10 to the negative fourth equals 1 over x minus 0.00268. We're going to add 0.0268 to both sides. That plus 0.008, 0.003281 equals 1 over x. Check it out. Ain't that pretty? Now remember, you got to get x out of the denominator. If it makes sense to you when I say you just take both sides to the negative 1, that is awesome. If it does not make sense to you, that is also fine. What color do I want to use? Let's use this cool orange color. We haven't used that. We're going to multiply both sides by x to get it out of the denominator. 0.003281x equals 1. Divide both sides by 0.003281. X equals 305 Kelvin. At what temperature is the vapor pressure of water 40.1 millimeters of mercury? We know that that is well below the boiling point. The normal boiling point is 100 degrees Celsius. At 100 degrees Celsius, the vapor pressure above water is 1 atmosphere, 760 millimeters of mercury. We have way less. In order to have way less vapor pressure above the surface of the water, the temperature has to be way less. And sure enough, it is. 305 Kelvin is approximately 32 degrees Celsius. So it's still warm. It's warm water, but it is not even close to boiling water. The boiling point of water is 100 degrees Celsius. All right. So that is your nice review of Clausius Clapeyron. And now we start new material. And here's where we're going to start talking about solutions. Now, just so you're aware, I'm aware that my voice does very strange things when I start talking about solutions. I do not say these words like a normal human being. And that is because I'm really trying to be very clear the difference between a solution, which is both the solute. And again, I know I'm saying that weird. I'm really emphasizing the endings so you can hear when I'm talking about these different things. The solution is both the solute, the thing that is being dissolved, and the solvent, the thing that does the dissolving. All right, so let's say, for example, you make Kool-Aid. And what do you do when you make Kool-Aid? You take a pitcher, which is actually just a beaker in this case, and you put all that red powder down at the bottom. Clearly, I'm making strawberry Kool-Aid. And then you put water in it. The red Kool-Aid at the bottom is the solute. That is the stuff that's being dissolved. It's the flavor, the sugar, it's the color. That is the solute. The water that you add is the solvent. That is the stuff that is doing the dissolving. And then you put in your glass stir rod and you stir, stir, stir. And you dissolve the solute in the solvent. And you are left with the solution. The solution is the Kool-Aid that you drink. So now, interestingly, let's say that you take this solution, you make up this solution of Kool-Aid, and you take a sip of it, and you're like, holy hell, this is way too sweet. So you add more water to it. You're like, man, I don't like it this sweet. It needs more water. So after you put in more water, you still have your solution, but it's a little less pink. That's not quite what I wanted, but hopefully you guys get the point. You still have a solution, but this solution has been diluted. So you can have a concentrated solution. It's got more solute to solvent. The solute to solvent ratio is greater. You have more solute to solvent than you have in a diluted solution where there is less solute per solvent. The ratio of solute to solvent has decreased. So just keep these terms in mind, concentrated versus diluted. So that is solutions. And we have to talk about these concentration units. We need to know if something is concentrated or if it's dilute and how we can use these solutions to calculate things because that's what we care about. So I'm going to go through some concentration terms and thankfully, most of them. Molarity gives us a symbol of big M. Big M is moles of the solute per liter of the entire solution. And again, I'm being really, really specific and careful. Molarity is moles of solute, the stuff that's being dissolved, divided by liters of the entire solution. Again, just so you know, in case you're like, what's happening? SOLN is the abbreviation for solution. So moles of solute per liter of solution. And interestingly, and why we're going to need a new concentration unit in just a little bit, molarity changes at different temperatures. Molarity is temperature dependent. That means that it can become more or less concentrated based on what temperature it is. And that is because volume is temperature dependent. This is something you guys know. I'm just bringing it to mind. You know that ice cubes, and that's a good ice cube. Ice cubes float in water because ice is less dense than liquid water. And that density, it's not the mass, but it's the volume that changes. So molarity is temperature dependent. If you want to talk about a concentration at different temperatures, let's say you take Kool-Aid and you put it in the freezer, you can't talk about the molarity. The molarity will change based on the temperature of the solution. So if we're doing things at vastly different temperatures, we need a new concentration unit. Just remember that if I say that something is 6 molar, just so you know what I'm saying, 6 molar, you need to remember that that means that there are 6 moles of the solute in every 1 liter of the solution. In my opinion, that is a conversion factor. You guys maybe have wanted to fight me on conversion factors since last semester. That's okay. But to me, that's a conversion factor. If I'm saying if I'm saying how many milliliters of the solution do you need to supply, 2 moles of the solute, you can use it as a conversion factor. And 6 molar versus, let's say, 1 molar. Remember, that just means that there's 1 mole of solute in every 1 liter of the entire solution. The 6 molar is concentrated. The 1 molar is the dilute. All right. So that's just a reminder of something that we did last semester. This is another concentration unit, is the percent weight. Sometimes I might forget and just put it in as mass. Remember, weight and mass for our purposes, not for all purposes, but for the purposes of this class, because we are not leaving planet Earth, weight and mass can be the same for us. So we're just simplifying that. So the percent weight of any given solution is equal to the mass, or again, the weight of the solute, typically in grams, divided by the mass of the entire solution, also in grams, times 100. We're going to do some calculations on this in just a little bit, but mass of the solute divided by mass of the solution times 100. An everyday or, like a normal person example of a solution that you deal with that is a mass solution is brass. You actually can have different concentrations. Brass, I believe, is a mixture of zinc and copper. You can't tell. It's a homogeneous solution. We're going way back. It's homogeneous because you can't tell that there's more than one thing there. I mean, you look at it and you're like, it's metal. But you can have different concentrations of zinc and copper in your brass. So I'm talking about like what a trumpet is made out of. And that is usually given in terms of a percent weight. So it might be something that is, 70% zinc. That means that 30% of it is copper. And if we assume that we have 100 grams of the entire solution, we can say, okay, we have 70 grams of zinc in that solution and 30 grams of copper. Next up, we have the percent weight volume. This is the one that I'm pretty sure, at least me, and I'm pretty sure most other chemists use all the time. And that is that the percent weight volume is the mass of solute in grams divided by the volume of the entire solution in milliliters. And then you can multiply that by 100. This is the one most typically used in chemistry because usually in chemistry we deal with things in aqueous solution all the time. An aqueous solution is when we take something and we dissolve it in water. So your best example of a real person thing is IV saline. Right? You go to the doctor and you have to be put on like IV antibiotics, or you need an IV to deliver medications, or let's say you're dehydrated and you need to get IV saline to rehydrate you. You cannot put straight water into your veins. That's no bueno. you would bad things would happen if you put straight water into your veins. So you put in IV saline. IV saline is 0.9%. And that is a weight volume percent of sodium chloride in water. Now, what does this actually mean? It means that, to me, this is a conversion factor. I don't like using using algebra. I can. Don't get me wrong. I can do it, but I don't like it because I like conversion factors. 0.9%. Think about it like this, because I've had students get this wrong, and so I'm trying to really explain so that you don't get misconceptioned. If you got a 0.9% on an exam, okay, that would be devastating. That would absolutely be devastating, but just bear with me for a second. 0.9% on an exam means that you got 0.9 points, so 0.9 grams of solute out of the entire exam, which is 100. So don't do weird things like multiply by 100 or divide by 100 in your head. 0.9% means 0.9 grams out of every 100. Every percent is out of 100. All right, think about it. Per century is what really you can think about, but a percent is always out of 100. And you guys know you're used to getting grades on exams. So a 0.9% would mean that you got 0.9 right out of the total that you could have gotten, which was 100. So 0.9% as a weight volume means 0.9 grams of solute, in this case sodium chloride, in every 100 milliliters of the entire IV saline solution. You can use it as a conversion factor. All right, next up we have a volume percent. Just like the other ones that we have done, this is going to be the volume of solute in milliliters divided by the volume of the entire solution, also in milliliters, times 100. So the absolute best example that I can give you for a percent volume that normal people deal with in real life, I don't even think it's sold anymore. It is a throwback to when I was in college. Bacardi 151 is a very, very, very strong liquor. It is rum that is extra concentrated. And what that Bacardi 151 means is that it is 75.5% ethanol. And that is a volume percent. That means that there's 75.5 milliliters of straight ethanol, the booze that you can drink, in every 100 milliliters of Bacardi. Because there's other stuff in there, right? Like any booze, and I think that this is a common misconception, even vodka, any booze that you drink, any liquor that you buy from the store, it's not 100% ethanol. If it was, everything would taste the same because ethanol would just be what it tastes like. But of course, all of these different alcohols have all kinds of other stuff in them to give them their own unique flavor. And this Bacardi 151, 75.5 milliliters of ethanol out of every 100 milliliters of the drink itself of the Bacardi. So that is a volume percent. Moving right along. Here is one of the new ones that we're going to get to. And it is the mole fraction. Mole fraction is given the symbol of capital X. And then you'll have a little subscript over here telling you what it is. Okay? So the mole fraction of solute in a solution is the moles of the solute divided by the total moles of solute plus moles of solvent. It's basically giving you the percent of solute, but not multiplying it by 100, right? Like every time that we've talked about percents, it's kind of been like part to whole. How much did you get right out of how much total you could get? Back here for the percent weight volume, how much solute out of the entire solution. So all of this, it's like a percent that you're not multiplying it by 100. You're just keeping it as a fraction. Moles of solute divided by the total. Moles of solute plus the moles of solvent. And interestingly, this is unitless. Moles on top would cancel with moles on the bottom. So this has no units. You can also give the mole fraction of the solvents, and that's just the moles of the solvent divided by the total. Moles of solute plus moles of solvent. And it is still unitless. So the mole fraction is just how much do you have that you're talking about, either solute or solvent, divided by the total. Okay. And now, my friends, this is the one that is by far and away the most important one to what we're about to do. And that is molality. I make my molality M very obvious. Just be aware that for me, it is lowercase and cursive. When I have to write it in an exam or something like that, I usually just make it italics. So just be aware, this is lowercase cursive m is the abbreviation for molality. And again, I make it really ridiculous looking in my handwriting. It's just italicized in print. Now, the reason we need molality is because, like I was talking about before, we've got molarity that changes based on temperature. So we can't talk about a solution at room temperature and then talk about that solution at near the freezing point because the molarity will change. So we need a new unit that is temperature independent. It does not change based on temperature, and that is molality. molality is equal to, it is the weirdest one. Okay? I can't help it. I didn't come up with it, but it's weird. It is moles of solute divided by kilograms of solvent. Okay, you can see why it's super different. Every other one, except for mole fraction, but every other concentration unit has been moles of solute to the entire solution or grams of solute to the entire solution. This one is moles of solute to kilograms of solvent. That's kind of weird. So it's just something that you really need to take into account. We're going to deal with it. Okay, good. The next slide. We're going to deal with it in two different ways. Okay, so there's a lot of stuff going on this slide. Just take a second. To be honest with you, what I think I'm going to do is I'm going to copy this and then I'm going to paste this and then I'm just going to this down here. I'm going to get rid of this. That'll give me more room. Where in the world? I wish you guys could like see the whole setup that I got going on here. It is insane. And I seriously lost. Oh, there it is. Delete. I'm an idiot. Okay. So, we're going to use this molality the two different ways. The first way that we're going to use this is basically what I'm calling as an equation. Okay? We are saying what is the molality? And again, if you remember to last semester, we did the same thing. We've actually done this several different times. We've used density as an equation as well as a conversion factor. We've used molarity as an equation as well as a conversion factor. And now here we're using molality as both an equation as a conversion factor. So how do you know when you do both or when you do which one? When the question says, what is the molality? Use it like it's an equation. We know that the molality is equal to moles of solute divided by kilograms of solvent. So what is the molality? We're going to figure out how many moles of solute we have, plug it into the numerator, figure out how many kilograms of solvent we have, plug it into the denominator, and solve. All right, so we have a solution. And it is made by dissolving 5.67 grams of sodium chloride, that is the solute, in 500 grams of water, that is the solvent. So we're going to take 5.67 grams of solute sodium chloride and convert it into moles. If I were in class right now, I'd be like, so what do we need in order to do that? And someone would say molar mass. And I would say, yes, that is accurate. The molar mass of sodium chloride, I've got my periodic right here, 22.99 plus 35.45 gives us 58.44 grams of sodium chloride in every 1 mole of sodium chloride. 5.67 divided by 58.44, 0. Worrying about significant figures. Lost my cursor. Oh no, come on back. Oh ho ho, this is less than ideal. There we go. 5.67 has 3 sig figs. So I'm going to make sure my answer has 3 sig figs. 0.0970 moles of sodium chloride. So check, check. We've got the top part of our fraction, 0.0970 moles of sodium chloride. Divided by 500 grams of water. There's 1,000 grams in every 1 kilogram. I don't know why I'm doing this on my calculator. Here is my neurodivergence coming through. 0.5 kilograms of the solvent. 0.0970 divided by 0.5 gives us 0.194 molal is how you say that. 0.194 molal is the concentration of this solution. Right? So there we're just using it like it's an equation. Figure out the top, figure out the bottom, divide the two. And now I know who is going to struggle with this hardcore, and it just is going to crack me up. As a conversion factor, we're going to use it as a conversion factor because the question is giving you the concentration. 0.999 molal means 0.999 moles of sodium chloride in every 1 kilogram of the solvents. It's a conversion factor, my friends. Two different things are set equal to each other with different units. 0.999 molal means 0.999 moles of sodium chloride or 0.999 moles of the solute in every 1 kilogram of the solvent. So this solution has 0.999 molal. If there are 1,255 grams of the solvent, how many grams of sodium chloride are there? Straight dimensional analysis. 1,255 grams of solvent is where we're going to start the dimensional analysis. We know that there are 1,000 grams in every 1 kilogram. Now we can use that molality as the conversion factor. Every 1 kilogram of the solvent is 0.999 moles of sodium chloride. And from the last slide, we know that every 1 mole of sodium chloride weighs 58.44 grams. I have been trying to get you guys to do it this way for molarity since last semester. Some of you guys do it no problem. Rock on. Some of you guys who shall remain nameless just keep fighting with me about dimensional analysis. And that is more power to you. I don't care how you solve things, but good Lord, are you making your life harder? All right, so 73.27 grams of sodium chloride. 1255 has 4 significant figures. Our answer will round to 4 significant figures. 73.27 grams of sodium chloride. So molality can be used as both an equation as well as a conversion factor. Use it as an equation when you're solving for the molality. Use it as a conversion factor when you are given it. Or don't. I don't care how you solve these problems. I'm trying to break it down for you in the easiest manner I can. If you want to come up with some weirdo way to solve it, more power to you. All right. So now, I don't have this answered on my cheat sheet over here. So we're going to have some fun. We have an aqueous solution. Aqueous again means that we know that the solvent is water. Of hydrogen peroxide, and just for funsies, I know it's H2O2. You probably don't know that, but H2O2. And we know that it's 30% by mass. So that means that it is there's 30 grams of hydrogen peroxide in every 100 grams of the total solution. That's what 30% by mass means. Again, just like you gave yourself 30% on an exam, that would mean that you got 30 right out of 100 total possible. 30% by mass means 30 grams out of 100 possible. And the solution has a density of 1.11 grams per milliliters. We want to know, what is the molality? Molality is moles of solute divided by kilograms of solvents. Mole fraction, I'm going to say that it's the mole fraction of the solute. That's moles of the solute divided by the total moles of solute plus moles of solvent, unitless. And molarity. Molarity is moles of the solute divided by liters of the solution. So now the reason I wrote these all out is for these kinds of questions, you can see that like you've got the same thing in many different places. So just make sure that you keep your pieces and parts out there in front of you so you don't have to like resolve the wheel every time. So, one thing is that we actually need to assume something. I didn't tell you how much of the aqueous solution you had, and you don't actually need to know how much of the aqueous solution you had. All of these terms, it doesn't matter the amount. So I'm going to I'm going to assume an amount. I'm going to assume an amount that makes my life easier. That assumption is we're going to assume that we have 100 grams of the solution. Now, again, be careful. I'm not saying we have 100 grams of water. I'm saying that we have 100 grams of the entire solution. If we assume that we have 100 grams of the entire solution, that means that we have 30 grams of hydrogen peroxide and we have 70 grams of water. Because when you add them together, you get the total. So let's take our 30 grams of hydrogen peroxide and convert it into moles. That's going to be what our pink answer is. Moles of solute. We need it for all of the things. So hydrogen peroxide 1.01 times 2 plus 16 times 2. Molar mass is 34.02. 30 divided by that, 0.882 moles of hydrogen peroxide. So again, we now know the pink part for all of that. Let's convert 70 grams of water. That's the solvent. So the solvent is water. The solute is hydrogen peroxide. And the solution is both of them together. So let's take 70 grams of water. There's 18.02 grams in every 1 mole. Wait a minute. What am I doing? I want that eventually. All right. I'll solve for mole fraction. This is 70 divided by 18.02, 3.88 moles of water. All right, I'm going to highlight this in a different color. That's going to be here. All right, so now we have our pink for all of the things. We've got our bright blue for one of the things. Let's solve for kilograms of solvent. Oh, we know that we have 70 grams of the solvent. And we know that there's 1,000 grams in every 1 kilogram. Again, I can't not put this on my calculator. 0.0700, because I'm keeping 3 sig figs, kilograms of water. So this is a new piece. That's going to go right there. So we know what the molality is now. I have to calculate it, but we know what the molality is. We know what the mole fraction is. We have to plug things in, but we know what it is. Last but not least, we need to figure out the liters of the solution. Well, what do we know about the solution? We know that we have 100 grams of it. And we know from the density that there's 1.11 grams of the solution in every 1 milliliter of the solution. And there's 1,000 milliliters in every 1 liter. 100 divided by 1.11 divided by 1,000. 0.0901 liters. I'm going to highlight this in a new color. Oh, I'm going to make it green. Now we know that bottom part. Now we just have to plug things in. Okay, so I'm not going to talk too much about this more in class. All right, I don't think that this kind of question is particularly challenging. You just have to make sure that you have the right pieces out. Keep in mind, though, that the homework for this chapter, I make you do this problem, these kinds of problems, a lot. I make you do them in the homework so that they come to you for as second nature on the exam. Take it seriously. Don't just cheat. Try to solve it yourself so that when you get to the exam, this is a softball question. Because, in my opinion, it really is a softball question. This isn't requiring a whole lot of conceptual brain work. This is more just put the pieces down, you know? Anyways, moles of solute is 0.882 divided by kilograms of solvent, 0.7, gives us a molality of, oh, 0.07. I just typoed myself. 0.882 divided by 0.07, 12.6 molal. Mole fraction, I'm just going to do it on my calculator. Hopefully you guys will be able to figure it out. But 0.882 divided by the total of 0.882 plus 3.88. I got 0.185 is the mole fraction. Remember, it does not have any units associated with it. Last but not least, we have the molarity. 0.882 divided by 0.0901. And I got 9.79 molar. Let me just take a double check and look at this, make sure that it all makes sense. 882 over 07. Yeah, yep, yep. So again, not particularly challenging. It's got like a couple of new tricks to it, I guess, if you want to, say that they are tricks. What color haven't I used? This, I guess, is the trick, recognizing what 30% means and then assuming that you have 100 grams. I guess that's the trick to it. The other thing is if you have 100 grams of the solution and 30 of those grams are made up of the solute, then the rest has to be made up of the solvent. So that's where we got this 70 grams of water from, because 30 plus 70 equals 100. All right. So now I'm just going to keep on barreling. Colligative properties. Colligative properties are very important. There are 4 of them. We're going to go through all 4 of them. I spend more time on some, less time on some, but there are 4 colligative properties. And what a colligative property is, it is a property of the solution that is different than the properties of the pure solvent. So the second you take water and you dissolve something in it, some of its properties change. It's not pure water anymore. It's water with stuff in it. And that stuff in it changes some of the properties. And by how much that property changes, it doesn't matter what is dissolved. It matters just the concentration, the number of solute particles, not the type of solute. It doesn't matter what you put in there. It just matters how much stuff there is. Get into that in a little bit, but these are the colligative properties. So we've got to give ourselves a quick reminder on how things dissolve. I've been doing this with you guys again since last semester because I knew that this very day was coming. How do ionic compounds dissolve in water? And I'm talking about soluble ionic compounds. I'm not talking about the weird ones that are not soluble. Remember, I gave you out those rules last semester. Don't worry about that. Assume that everything I'm giving you is soluble. How do ionic compounds dissolve? Ionic compounds dissolve by dissociating. So, sodium chloride is a solid. When you put it into water, it dissolves. You guys know that. Salt water has sodium chloride dissolved in water. That sodium chloride dissolves by breaking into its particles. We did this a bunch when we did the net ionic equation stuff, the total ionic equation, cross out the spectators, net ionic equation. Ionic compounds that dissolve dissolve by dissociating. Don't lose your charges. Sodium is a +1 cation. Chloride is a -1 anion. And if you guys remember, I said 1 particle of sodium chloride goes in, but how many particles of ions come out? And in total, it is 2 particles. The ideal Van Hoff factor for this compound is 2. And I'll talk about that on the next slide, but the ideal Van Hoff factor is just how many particles does it dissolve into. The ideal Van Hoff factor for sodium chloride is 2, because 1 sodium chloride unit dissolves into 2 particles. So again, if we were in class, I would say, all right, what about iron 3 nitrate? One of my favorite compounds. Iron 3 nitrate is soluble in water. First, I would make you tell me what its formula is. Iron 3 nitrate means iron has a +3 charge. Nitrate is one of the polyatomic ions that you must have memorized. If you don't have it memorized by now, we've got problems. Nitrate is NO3 and it has a -1 charge. So we need 3 nitrates for every 1 iron 3. So then the next question would be, well, how many particles does that dissolve into? Also known as, what is the ideal Van Hoff factor for iron 3 nitrate? The ideal Van Hoff factor for iron 3 nitrate is 4. It dissolves into 1 iron 3 ion and 3 nitrate ions. 1 plus 3 is 4. All right. So please, this is important. Ionic compounds that dissolve in water dissolve by dissociating. Acidic compounds. Hydrochloric acid is an acidic compound. Hydrochloric acid dissolves by ionizing. And for right now, we can say that it ionizes into a proton and a chloride. So again, what is the ideal Van Hoff factor for hydrochloric acid? The ideal Van Hoff factor is 2. 1 unit of HCl goes in and 2 particles come out. All right. Last but certainly not least, what happens to covalent compounds when they dissolve? Absolutely nothing. All that happens is a phase change. These are also known as non-volatile, non-electrolytes. All of these that come above, acidic and ionic compounds, those are electrolytes. They're electrolytes because electricity travels through water that has ions dissolved in it. Let me say that again. Water conducts electricity when it has ions in it. So ionic compounds make ions when they dissolve. Acidic compounds make ions when they dissolve. So they're electrolytes. It carries electrical charge through the water. Covalent compounds, on the other hand, it doesn't form any ions. So it's not electrolyte. It's not an electrolyte. You can't have electricity flow through water that does not have ions in it. If you just dissolve a covalent compound in water, it is not conductive. Non-volatile does not mean does not explode. Okay, that is incorrect. That is a very common misconception. People think that volatile means explode. It doesn't. Volatile just means evaporates readily. So covalent compounds typically do not evaporate readily when they are dissolved in water, we'll say. So a covalent compound is also known as a non-volatile non-electrolyte. So my favorite covalent compound is sugar. Ooh, that's a solid. When sugar dissolves in water, and we all know it does, we put sugar in our coffee, sugar in our tea, sugar in our Kool-Aid. When sugar gets put into water, it dissolves. You can't see it there. It makes a homogeneous solution. but all that happens is it changes its phase. No ions are formed. So what is the ideal Van Hoff factor for any covalent compound? It is 1. What in the world just happened? That was very odd. It is just 1. 1 particle or 1 unit of sugar goes in and 1 particle or 1 unit comes out. So the ideal Van Hoff factor for this covalent compound is 1. That's how you spell Van Hoff factor. So again, for ionic compounds, the ideal, and I'm being very careful. I don't know if you guys have noticed this or not. I keep saying ideal Van Hoff factor. That should give you a clue that there is such a thing as a non-ideal Van Hoff factor. We will get there. But for right now, everything is ideal. Ionic compounds have an ideal Van Hoff factor equal to, I'm just going to write it out, equal to the number of ions in the compound. So let's say like magnesium sulfate. Without writing out that whole formula, thinking about how it dissolves, I just want to know what's the ideal Van Hoff factor for magnesium sulfate. The ideal Van Hoff factor is the number of ions that make it up. Magnesium sulfate has a magnesium ion. It has a sulfate ion. That gives me an ideal Van Hoff factor of 2. What's the ideal Van Hoff factor for, oh, I don't know. I was just about to give one that came potassium. We'll do potassium nitrate. That's fine. Potassium nitrate. The ideal Van Hoff factor for potassium nitrate is 2 because it's made up of a potassium ion and a nitrate ion. So you don't have to go through and do that whole formula to figure out the numbers. Just look at it and think about it. So for example, I'm trying to come up with one more. Let's do copper 2 chloride. The ideal Van Hoff factor for copper 2 chloride is 3. 1 copper, 2 chlorides. Acids I'm not going to really get into, but covalent compounds have an ideal Van Hoff factor of 1. Always, always, always. Any covalent compound is always going to have an ideal Van Hoff factor of 1 because covalent compounds don't break apart into anything. So 1 compound goes in, 1 particle comes out after it dissolves. So now, let's get into it. Here are your 4 colligative properties. Freezing point depression. That's the only one I'm going to talk about today. The other ones are very similar, but freezing point depression is FPD. What that means is the freezing point of a solution is less than the freezing point of the pure solvent. Freezing point depression. The freezing point of a solution is less than the freezing point of the pure solvent. This is why we salt the roads in the wintertime. Although right now, I woke up this morning and it was negative 4 degrees Fahrenheit. Really cold. Salting the roads doesn't work when it gets this cold. There's a limit. There's a limit to this, okay? We can't salt the roads enough to lower the freezing point that much, but that's what happens. You put salt down on the roads when it gets cold out, and the freezing point of that solution, that salt water mixture on the roads, is less than 32 degrees Fahrenheit. So you can go out at like 20 degrees Fahrenheit and the roads will just be wet because the freezing point has been decreased enough that it hasn't frozen. The freezing point is less than the freezing point of the pure solution. That's why you can like make slushies and stuff like that in the freezer because you're making a solution and it's going to freeze at a lower temperature than what your freezer is set at. That's why it kind of gets that like mixed texture. Same thing with like ice cream. It doesn't form that solid, hard ice block. It forms a creamier mixture because its freezing point is less than the freezing point that your freezer is set at. Boiling point elevation, we'll get there later, but I'll tell you now, the boiling point of a solution is greater than the boiling point of the pure solvent. So I made spaghetti noodles yesterday. I put salt in my water. It actually causes it to boil a little bit high. It is not a significant change, okay? Boiling point elevation, not a significant change. We don't use that in our daily lives very often. Um, freezing point depression we use a lot, but boiling point elevation is a much smaller change. Then we'll talk about vapor pressure lowering and osmotic pressure. The big two are freezing point depression and boiling point elevation. So, freezing point depression. Here is the equation for it. Delta T equals the ideal Van Hoff factor times the freezing point depression constant times the molality of the solution. So, the freezing point depression constant is for each different solvent. We're going to be dealing with water for the most part, but I'm probably going to throw it at you that it's not just water, depending on my mood and depending on what lab I do with y'all. I'm still thinking. But anyways, freezing point depression constant is solvent dependent. Like it changes based on what solvent you have. You can have water, and the freezing point depression constant for water is 1.86 degrees Celsius per molal. I am so sorry. That should be lowercase cursive m, not just printed m. So every molal, every increase in molality lowers the freezing point of the solution by almost 2 degrees Celsius. That's a lot. 2 degrees Celsius is a lot. So every change in that concentration, every time you go up from 1 molal to 2 molal to 3 molal, the freezing point changes by almost 2 degrees Celsius. All right. Oh, and I is the Van Hoff factor, so you got to know if you're putting an ionic compound into it or a covalent compound. And the delta T, this is going to become really, really important. The delta T is the change in the freezing point from the pure. Okay, so best way to do it is just to do it. And to be honest with you, I'm done talking. It's almost been an hour and a half, and I'm done. If 2.3 grams, oh, let me find my cursor. I have 3 monitors at home. That's why my cursor keeps going all over the place. But if 2.3 grams of C6H12O6, that has a molar mass of 180.18 grams per mole, is added to 500 grams of water, what is the freezing point of the solution? So let's break it down into its pieces. We have 2.3 grams of the solute. And we are adding it to 500 grams of water, which is the solvent. We know the freezing point depression constant for water is 1.86 degrees Celsius per molal. And we know that the delta T is equal to the ideal Van Hoff factor times the freezing point depression constant times the molality of the solution. So I'm going to just figure out each one of these things and then plug it in. So let's start with the ideal Van Hoff factor. The solute is C6H12O6. Is that ionic or covalent? Answer is that it is covalent. It is covalent because those are all nonmetals. The ideal Van Hoff factor for any covalent compound is 1. It does not break apart into its ions because it doesn't have ions, it's covalent. The freezing point depression constant for water is 1.86 degrees Celsius per molal. And then the molality of this solution is moles of solute divided by kilograms of solvent. So let's figure out the molality. We have 2.3 grams of the C6H12O6. We know that there's 180.18 grams in every 1 mole of that sugar. I was super lazy. I should really write my labels down. Don't come for me, all right? 2.3 divided by 180.18, 0.0127. I'm going to keep my sig figs until the end. I'll keep 0.0128. Moles of sugar, C6H12O6. All right, so check. We've got our top part of our fraction here. I'm using molality as not a conversion factor. I'm using molality as an equation right now. We have 500 grams of the solvent. That is half a kilogram. And again, I just did that in my head. Hopefully that isn't that hard for you guys to wrap your head around. But we have 0.0128 moles of the solute divided by half a kilogram of the solvent. Oh God, 0.0128. I'm typoing left and right. Divided by 0.5, 0.0256. Molal. Well, now we just plug it in. The change in temperature, delta T, is equal to the ideal Van Hoff factor times the freezing point depression constant, and I'm going to keep my units in this for a second, times 0.0256 molal. The change in temperature is 1.86 times 0.0256. 0.048. Let's focus on units first. Molal cancels with molal. We're left with units of degrees Celsius. But here's the thing. That's not your answer. What is the freezing point of the solution? The freezing point of the solution is not 0.05 degrees Celsius. Because the whole point is that the freezing point of the solution is less than the freezing point of the pure solvent. The freezing point of pure water is 0. The delta T is the change in. That is the amount by which the freezing point has been lowered. I'm going to write that down because I say it aloud. Delta T is the amount by which the freezing point is lowered. So you have to be smarter than your answer. The freezing point of the solution is the freezing point of the pure minus the amount by which it's lowered. So the freezing point of this solution is 0 minus 0.048. The freezing point of the solution is negative 0.048 degrees Celsius. Be careful. Don't lose that last step. The delta T is not the answer. The delta T is the amount by which the freezing point is lowered. It is not the freezing point of the solution. It's just the change in. Delta means change in. All right, I'm going to stop there because I am done. Thank you very much for hanging out with me and taking all your time to watch this. I appreciate it. I just got a text message while I was working on this that we will be getting back to school by normal on Thursday. So I will see Eastern on Friday. Don't worry about printing anything for lab. Like I said, I haven't even been up there since last week, and so I'm not entirely sure what I am going to be doing in lab. That being said, friends, you've got two things due to me. You have that stoic review. I've only gotten that from one student. They're amazing. They like to hand things in early, much more than the rest of y'all do. So, anyways, I've got one stoic review. The rest of you owe me your stoic review on Friday. And you owe me your Vesper worksheet, valence shell electron pair repulsion. You owe me that pre-lab and that post-lab where you go through and you draw all the Lewis structures, double check for formal charges, give me the shape, give me the bond angles. So please don't forget, you owe me all of that work on Friday. Watch these videos, take the time to learn. I will just keep going straight on when we get back to school on Monday. Well, Friday for my Eastern students, Monday for everybody. I will assume that you have watched and taken notes on this. I won't assume that you're an expert at it, but I will assume that you've at least watched and taken notes on this stuff. We're going to start hardcore with nice review stuff. So keep up with the homework, keep up with the extra credit. I am not falling behind. We are there. All right, friends, stay warm. It is supposed to continuously to be just brutally cold. Stay warm. Email me if you have any questions. I'll see Eastern on Friday. I'll see the rest of y'all on Monday. Thanks so much.